Thank you so much for waking up and coming here. I will try to make a presentation that is a bit visual, such that we don't get too much into the math details, but I will try to explain as much as possible on how we use AI on this particular topic. And furthermore, look forward to having your questions afterwards. So first of all, a little bit about myself. I have a background in statistics and in engineering in general. I've been through big tech companies like IBM and Google. And then I spent a bit of time in an AI company called Snips in France, was just bought actually by Sonos. And 4 years ago, actually almost exactly 4 years ago, I decided that we needed to focus our attention to something very, very urgent, which is climate change. And the way we're thinking about this in general at Tomorrow is that too many people are wasting their talents at big tech companies, and given the urgency of the topic, we really need to focus on climate change. So at Tomorrow, we're merging two kinds of people: the ones who know a lot about climate change and the ones who know a lot about AI and technology in general, to put those two in the same place, and amazing things happen as soon as you do that. So in a nutshell, our mission is to get the world to understand and reduce their carbon footprint by building the right tools that educate them and then empower them to take action. The first tool that was built is called electricityMap, which I'll show in just a second. And there's another one which I won't focus on today, which is codenamed right now the Tomorrow app, and which computes your personal carbon footprint, but completely automatically with a limited amount of user input. And it's coming out in a few weeks, so just stay tuned and follow us on social media if you want to know more. So the proposed solution to climate change that you will see a lot of places is just let's electrify everything: electric planes, electric heating, electric cars, everything. The problem is always, wait, but where does that electricity come from? Because if you generate electricity still with coal, then how much have you actually won by electrifying transportation, for example? And unfortunately, this is how electricity is generated today. So if you look at this thing, this is a big machine that mines lignite coal in Germany. And just to look at the scale of this, you can see here there's a small tractor here. So look at the size of this thing. I find it very visual. And if you want the numbers, 40% of the electricity worldwide is still generated by coal. 2/3 of the increase in CO2 emissions last year came from increase in coal as well, or emissions in the power sector. And this is, of course, a very, very big problem here. So we built electricityMap, which I'm going to show quickly a demo of for those of you that don't know it. Let's do it like this. Boom. So this is publicly available, and anyone can go and check this thing out. I'll put it in dark mode just because it looks cooler. Maybe it doesn't work. All right. That's the one, actually. All right. So what this thing showcases is, in real time, if you were to take 1 kilowatt-hour of electricity from your electricity plug, say, to charge your Tesla, how much greenhouse gas would be emitted in that process? And the greener the country, the more greenhouse gas, the less greenhouse gas, of course, is emitted. And right now, I'm looking at Ireland, which looks surprisingly green actually right now. And I wonder if it's because the wind is blowing. And so we have a small feature where we can show the wind layer. We'll see if it works. And you can see, for example, here the wind is blowing quite a lot on Ireland. And when you click on it, you will see here, the energy breakdown. So how the electricity is generated currently. The gray area you see here showcases the wind capacity. So if all the wind turbines were generating electricity, that blue bar would fill the whole bar. And you can see right now it's 70% of the electricity from Ireland that comes from wind. And if you look at the history, you'll probably see something interesting. You can see here the carbon intensity was reduced significantly by the wind here, the wind gust, the wind production augmenting, and the gas production, which is the red part, being reduced. So this tool is open source in the sense that anyone that sees a country that is missing on the map can code a system that fetches the data, puts it on the platform, and then all those computations happen. So going back to I'm going to close this one. Going back to the presentation here, how does it work exactly? Because the unique thing here is that we're using so-called flow tracing to figure out where the electricity comes from. So it takes into account the imports and the exports using 3 simple rules. Rule number 1, within an area, we consider things to be a copper plate, which means electrons are immediately everywhere on that area. The second thing is that the imports that impact the consumption mix. So it means that when you're importing electricity from somewhere, you're getting a proportional share of that electricity inside your area, which means that, for example, if you are 100% renewable in an area and you import 50% of your electricity from something that is not renewable, in your own area, you will be 50% renewable. So you get diluted by an import. And last thing on the exports, you cannot choose which electrons you send out to the neighboring countries, which means that you're sending out a share, a proportional share of your electricity, which means in turn that you're not diluting yourself as you export, because if you have a mix that is 50-50, you will export a 50-50 mix, which doesn't change your own mix. And with those rules, you can basically set up a linear system of equation that you invert, and they can solve this system to figure out what is the mix of each country and what is the carbon intensity of each country. So what you're looking at here is energy conservation in general, and then we go to CO2 conservation. So in a nutshell, what we say here is that everything that you consume locally must be either produced locally or must come from the neighbors. So far, no mystery. But as soon as you go to CO2 here, then what you're saying is that the power that will be consumed is applied a carbon intensity factor, which is the color on the map. This is what we want to solve for. And this is going to be equal to a scalar product of the production units multiplied by their carbon intensity. For example, wind has an IPCC factor of roughly 10 grams per kilowatt hour, coal is 700. So you make this scalar product here. Then you do the same thing here with the imports, but using the carbon intensity of the neighbor as a factor here. And then you subtract the exports with your own carbon intensity, remembering that you do not get diluted as you export. So you export stuff with a color which is your own. And you can solve this. Basically, you can put this term to the left side, this term to the right side, and then you end up with a linear system of equation, AX equals B. You invert the matrix, and that shows you all the colors on the electricity map. An interesting thing here is that this takes into account loop flows as well, because you can have a country that imports from another country that imports from this first country, right? You can have circular systems here. And this system, because it basically solves a graph system, is solving also for that. So this is going to be important for what I'm going to talk about next. But the end result is, if you look at what we call the physical origin of electricity in Denmark, for example, which is highly interconnected to the neighboring countries, you will, of course, see a lot of wind energy here. But you'll also see some nuclear energy here. And this is imported from Sweden. And you have some hydro energy here. Denmark is flat as a pancake, so there's no way you're going to have hydro there, but it's important from Sweden and Norway. And those are super interesting insights, because you shouldn't just look at your own country when you try to optimize things. You should also look at the interconnectors, especially with intermittent renewables. When the wind is not blowing, how do you procure that extra energy? Is it storage or is it interconnectors? In this case, you can definitely see that when the wind wasn't blowing, we were filling it up with hydro from the neighbors, but also increasing local coal consumption here. And of course, it goes without saying, you'd rather want hydro instead of coal. So now to the big problem, which is marginal origin of electricity. So there's a simple use case, which is, I have a Tesla at home, I'm charging it. Where does that extra energy come from? And the thing is, in the power system, when you increase demand, it's not all the power plants that will generate additional electricity that will go to your Tesla. It's only the last power plant that has been dispatched, or the cheapest one that still has capacity. And this is because on the electricity system, you have here power plants that are dispatched in a certain order, which is based on the price here. So the cheapest to be dispatched are always renewables, because when the wind blows, you don't have a choice. You just take that wind energy, and often it's very cheap. And then you have nuclear, then you have the fossils at the top, which are the most expensive ones. And the real tricky part is you don't know that curve here. So when you're charging your Tesla, ideally we could say here, the current demand is here. So if I am asking for a little bit more electricity, I'll be here. Well, it's going to be coal. Therefore, the footprint of the electricity, the additional footprint of the electricity I'm consuming is coal. But this curve is secret because it's market specific. So we are trying to figure out a way, I'm going to walk you through it in this presentation, how we actually figured out how to estimate this curve using machine learning. So in a nutshell, again, because this is a bit tricky, the color you see on the electricity map is called the average carbon footprint of electricity consumed. The other one is akin to a sensitivity analysis. It means if I have to ask a little bit more electricity, where does that additional piece come from? And those two are very, very different. So what has previously been done is that we look at changes in local generation historically, and we look at changes in local demand. We basically fit a linear regression and look at the factor between them. Because what it tells you is, if the load, so the demand is changing, how will the local generation react? And the G here is so-called the marginal emission factor. It's the carbon intensity of the additional unit of electricity. The problem is that this thing doesn't take into account imports, exports. It's one value for the whole year, which is problematic because there's no change of charging your Tesla when the wind blows or when it doesn't. And lastly, it doesn't take into account external effects. For example, when the wind starts to blow, it augments your changes in generation because suddenly you're generating wind, but it has nothing to do with you charging your Tesla. And this is unfortunately not captured in this model. So what we're using instead, here we go, is a more complicated, slightly more complicated linear model where we are looking at two additive components here. One is f of z, so z would be a feature vector. That feature vector represents the market conditions. For example, how high is the electricity price? Is the wind blowing? What is the season we're currently in? And so on and so forth. And that part captures changes in the generation, which are independent of changes in demand. So that would be exactly what I told with the wind just starts to blow, okay, the generation is going to change, but it has nothing to do with a change of load here. And then we have this function, g of z, again parameterized with market conditions. And the g is going to be the marginal emission factor, but it's going to vary at each hour based on the evolution of the z. So it's driven by an external mechanism here. And if you want a bit of mathematical intuition about this, you can look at this as a Taylor expansion around a fixed point. So you're saying you have a preferred operating point of the electricity system. You're trying to deviate a little bit from that by, for example, asking a little bit of extra electricity with your Tesla. And then you see how it reacts. And the other way to look at this is that is the first response, the first order response of a finite impulse response. So you're giving an impulse of a slightly increased demand, and you're seeing how the system reacts. So going back to, so maybe a bit of the overall methodology we're going through here. We have this function here. We're creating a linear model to reconstruct all the historical data we gathered on electricity map for the whole European grid. And we're trying to say for each changes that happen historically, are we able to reconstruct this using this function? And then we can extract this piece of the parameters, and this is going to tell us the transfer function that comes specifically from the demand change. So Z is a feature vector, as I mentioned, wind speed and area, market prices. I think we have like 500 features or something like that because we're putting the market prices in each of the areas of Europe, the average wind speed in each of the areas of Europe, the temperature forecast, everything. So this is the linear form, just putting it as a linear model. And then we use L1 regularization in order to select all the most meaningful features because those 500 features are way too much. And also you have a lot of local effects. The price in Spain is not going to impact, for example, the price in Sweden. And then we, again, use flow tracing and finalize. So I'm going to walk through a bit visually how this works. So this is reconstructing the past generation mix for a couple of production modes in France. For example, here you have the hydro. So you see the blue curve shows all the changes in generation, and the orange curve shows how we're able to reconstruct it driven by market prices and other things. And you have this for all of the different modes, and that enables us to say, on average, every time there's been an increase in demand, how did the local generation react? So normally it's a time series, but I just took an average picture here so you see a bit the trends. You see some interesting things. For example, here in France, you see that you have this brick here, which represents nuclear. So for example, when you increase demand in France, they will, to a certain extent, use nuclear to balance that load, which is unprecedented because you don't see it anywhere else. Great Britain, mostly gas, for example, here. So that's one piece of the equation because this still doesn't take into account consumption. Only takes into account how the local generation reacts, but not how the interconnectors react. So you can do the same thing with the interconnectors, and those are much, much more noisy. For example, here, this is Italy. We've broken it down by different zones, and this is an interconnector within Italy. And here, again, we're reconstructing in blue the changes of the interconnector values. So how much does the interconnector change as soon as you're increasing demand? And the orange curve shows how well we're able to fit it. And you can see it's very difficult to actually make a good fit for this. You can then visualize all of those averages over a year. So this matrix you have here to the right showcases the local generation, how it changes to a change in demand. This is the picture I showed you before with the French nuclear, for example. And here you see how the interconnectors change. So what you have on the left axis here is for a given change in a given zone, and how much does it impact the other zones? And on the diagonal terms here, you have how the local generation is. So in my own zone, if I change something, how much does it affect myself, so my own generation? And on the off-diagonal terms, you have how the interconnectors work. So for example, here in Denmark, you'll see that most of the electricity, marginal electricity, actually comes from Sweden. They're using the Swedish interconnector to balance their system. I won't go too much into details also because I don't have time, but this is only the first order. So it's in Denmark, how does the neighbors become impacted? But you can use the same flow tracing mechanism to go n order ahead of time. So you can see in the end, for example, that Denmark ends up having, I think, Finnish electricity here, if I'm not mistaken, in their system. And there's 2 orders away from Denmark. Exactly, so there you have it. And you also end up having, for example, here in the generation that the Danish mix actually impacts the Swedish hydro as you increase demand. And there you have the time series. So you have the carbon intensity in blue, which is the color of an electricity map again. And you see that the marginal one, the one that comes from the fact that I'm increasing my electric vehicle charge, is often lower since we are using low carbon neighboring electricity to balance the Danish electricity system. And this is exactly what the data tells you. You can look at it on average, again, using a box plot to see the volatility of the different systems. I won't go too much into details here. We have a blog post that explains all of that if you're interested. But an interesting application of this is we looked at if you had to install a wind turbine, where would it yield the maximum reduction of carbon? Because when you install a wind turbine, you will reduce something else when that wind turbine increases its production. So what you're removing is the marginal carbon intensity of a power plant. And you realize, for example, that if you install a wind turbine in Norway, you're removing low carbon electricity. So actually you're not winning anything. Whereas if you're doing it in Poland, for example, or Great Britain, we're guaranteed to remove fossil because it's on the margin. You will have a very, very high return on investment. So that is, in my opinion, how we should decide where to install renewable projects in general. Last thing I'll mention, electric vehicles. Of course, we should be charging them at the right time. This picture shows you the different carbon intensity per kilometer driven or by kilowatt hour used for electric vehicle charging. And you see there's a big, big discrepancy. Low carbon Sweden, because of hydro, is basically completely different from if you have a Polish electricity powering your mix based on coal. So we did some experiments and we've worked on research projects to do this. Very simply put, we create a forecast of the marginal carbon intensity, which you can see here in orange. And then you make an optimal dispatch algorithm to charge your electric vehicle at the optimal time. And you see very quickly, you have 10 to 20% emissions avoided, reduction in emissions based on this. And we're working with different car manufacturers to get this out. I'll show you a great animation that I love of electricity map over time. You can see the different countries are blinking so much based on the actual amount of renewable energy that is produced and how the weather conditions are changing. And our pitch to most companies would be, look at this, make sure that any device that you have in your company that uses electricity, use it at the right time. Talking electric mobility, we're also talking a lot about data centers. When you launch your AI computations during the night in the cloud, why not pick the data center that is the greenest right now, and also pick the time where the electricity is the greenest right now. And so we put all of this into an API here, just api.electricitymap.org, which anyone can use. We have a free tier. And with that, I'll leave you with the end of my presentation. Let me know if you have any questions. Thank you.
Thank you so much, Olivier. Questions?
Thank you for the talk. Very nice. I think I have a question. How plausible is the linear setting in the case of how you use it, did you see that that's the case, or have you tried nonlinear methods?
So we are trying nonlinear methods right now. I think it's the amount of signal we're going to be able to extract from this is going to be increased as we move to nonlinear methods. So for now, it's just the first approximation we're using, but it needs to be improved indeed.
Does it explain a lot of the data that you're trying to explain, or is it a plausible assumption, or?
I mean, the way that I look at it is again, if we're looking at the stability of the system. So we're linearizing close to the fixed point. And so if you have small deviations, then the linear assumption is valid, we found out. But as soon as you make large deviation, this is where the nonlinearity really kicks in. And another way to put it, if you want intuition from the electricity system, is if you're just looking to assess the next wind turbine, where to install it, so like a small change compared to the total installed capacity, the linear assumption is valid. But if you're saying suddenly, I want to install 10 wind parks and double the capacity, then you're changing the system so much that the linear assumption is not valid anymore. And that this only tells you for very small deviation, like charging your car or maybe installing the next wind turbine, if it's not too big. But else, it doesn't apply anymore.
You had some countries which were gray, for example, also Switzerland.
Yes.
What is the reason for that? You don't have data for these countries?
Yes, or the data quality is not high enough. So for example, specifically for Switzerland, the energy mix that we're getting in open data is not covering to a sufficient extent the actual production mix. So we're missing some pieces in there, and therefore we prefer to put it gray. So if anyone can help us get access to better data, come see me after.
Yeah, thanks for the talk. I think that's great. It looks like some perfect insights for utilities, and there are smart grid goals and things like that. So how do you put these insights into action? Do you just count on individuals to take action when they see this data, or do you work with utilities to put that into action?
So we believe that a lot of the things we do need to go through the consumer, but also companies. And the way the two interact is especially on any device that is flexible and needs to use electricity on the right time. So if you look at, for example, electric vehicles, what needs to happen is that we need to have enough consumers that actually want to charge the electric vehicle at the right time. And then we need to have enough companies that can address that need. And that's why we're working on the two sides of the equation. The utilities are a bit the same. This is not a new idea to use electricity at the right time. Demand response has been there forever. The thing that is changing now is that the levels of renewable penetration are getting higher. And also the consumers are getting more and more excited and asking for those things. But the response from utilities we've got, it depends a little bit on the geographies we're looking at. But for example, in the Nordics, the infrastructure is fairly recent, very, very robust. So on their side, they prefer having copper in the ground than installing such systems right now. This is why I see it a lot driven by the consumer and CO2 reduction targets. This is where the thing is going to be driven from.
Thanks again, Olivier.
Thank you.